Here's an example of a quadratic function. So a quadratic function, like a quadratic equation, has powers of x up to and including x squared. So you can have x to the 2, x to the 1, and you can have a constant. And anything in that form is called a quadratic function. There are other ways to write it, though. For example, if we factor the one that we're looking at here, you can write it in this form instead. So if it can be written like this, we call it quadratic, but it might be written a different way. And in particular, other ways of writing it might be useful for other purposes. So consider the form we see here, x minus 3 quantity squared. Just by looking at this form, I can tell that the output from this function is always going to be positive, because after I plug in an x, I'm going to get something which might be negative, but then I'm going to square the result, and I'm going to get something positive. And the smallest value I could get out is if I plug in a 3, because then that will give me an output of 0. Because 3 minus 3 quantity squared is 0. So the smallest output I can get is 0, and every other output I get will be positive. So in particular, this 3 we see is the horizontal location of the lowest point on the graph of this function. Taking a look at the graph here, it's just as we described. The lowest point occurs when you plug in a 3, and every other value is bigger than that. This shape we see here is typical of a quadratic function, this U shape. Quadratic functions always have either this shape or this shape, a U-like that opens upward or downward. Here's another example. If I have x squared minus 4x plus 6, I can rewrite it a little bit. If I split up the 6 into two pieces, 4 and 2, then the first three terms here can be factored as x minus 2 quantity squared. So the 2 moves down to the next line, and the first three terms are being rewritten as x minus 2 quantity squared. And the same reasoning we used in the last example tells us that the lowest point on this graph will be when x is equal to 2, because plugging in a 2 will produce an output of 2 minus 2 squared, which is 0, plus 2, and any other value I plug in for x will produce something positive, plus 2, which will have to be bigger. So the lowest point on the graph is when I plug in a 2 for x, then this term is all 0, and that means the output is equal to this value, which is also 2 in this case. So the lowest point on the graph occurs at x equals 2, we can see. And if you look at this graph, in order to get it to fit on the screen, you'll see that the height actually lines up with y equals 2. So you don't see the entire positive y-axis here, only part of it. Here's another example. This time I have a coefficient in front of the x squared. So the first thing I'm going to do is pull that coefficient out. Factor it out from the entire expression. So that leaves me with 2 out front, and then x squared minus 2x plus 4 inside parentheses. And I can use the same trick we just did, where I split the constant up into two separate pieces. And the point of splitting it up the way I did is because the first three terms now are something that I can factor. In particular, these factor as x minus 1 quantity squared. And if I then redistribute this 2 everywhere, I have 2 times the quantity that's squared and 2 times 3. I'll simplify that 2 times 3 into 6. So can we tell from this what the lowest point on the graph is going to be? To get the smallest possible output, I want this part to be 0. I know it can't be negative because it's squared, so the smallest output will be when it's 0. And so that's going to happen when x is 1. And if I put in a 1, this whole thing will be 0, and the output will just be 6. 0 plus 6. So x equals 1, y equals 6 is the lowest point on this graph, as we see here. Again, this lowest point lines up with x equals 1, and right here, this is y equals 6. So any quadratic function can also be written in this form by doing some creative algebra like we did in the previous examples. So if I want to rewrite the function in this form, I call it the vertex form, and that's because these numbers h and k, those are the locations of that point that's lowest if the parabola opens upward, or as we'll see in the next example, the highest point if the graph opens downward. We call that point the vertex. And you can tell if the graph opens upward by looking at this coefficient, a. If a is positive, then the graph of this curve, which we call a parabola, opens upward. If a is negative, the graph opens downward. So here's one more example. Consider this function f of x equals negative 2x squared plus 5x. We won't go through the calculations here, but it turns out that you can also find the vertex by a formula we will learn soon. And that vertex right here is actually lining up with 1.25 for x. And there's a very easy formula for finding that x value, which we will cover shortly. This is our first example of a parabola that's opening downward, and the way we were able to predict that is because the coefficient in front of the x squared term is negative, in this case, negative 2.